appeared in Avi's talk. It's the same door. So I remembered very vividly standing in front of this door and before I knocked on the door, feeling that something very, very important is going to happen in my life. And lo and behold, it did. So I came in, and Michael told me, well, brain science is very, very interesting, but let me tell you about something really interesting. And he told me about all this stuff, Shor's algorithm, and that was 95. Shor's algorithm and BPP, and there was two-slit experiment and Turing machines, and it went on and on and on and on. And I remember getting out of this out of the room, out of this door, with two very strong feelings. One is, boy, I just met the smartest person I've ever seen, and two, I understood basically zero. I was very, very dizzy, but I did understand that this was really something very interesting, and that this meeting was very important in my life. And that was almost 30 years ago. And since then, we've had a roller coaster, a ride, a journey, a beautiful set of interactions, and I've learned so much from Michael in so many ways. I think Michael is not only a great scientist, but you're also a really great person, both in terms, you agree? Both in terms of humbleness and kindness, and in so many ways. I remember, so John was talking about helping to correct errors. So I remember in my first paper, we were about to submit it to Stock or Fox, and that was a Friday afternoon or something like that. And I discovered an error. And well, it was my first paper. I was about to cry. And I don't know if you remember it, Michael, but I didn't know what to do. And then Michael came by and helped me. And we somehow fixed together this thing close to the Shabbat. And so you're not only an excellent error corrector, but also an amazingly kind person, and helpful. And there's so many things that I can go on and on and on. But instead, I want to tell you about basically, so we have had so many beautiful things that I could talk about. So I wanted to tell you about two tales, two basically works, themes that me and Michael have been working about on. I want to, what is that? Computer is okay.
Yeah, I definitely not any help.
So wait, it's about the connection to this. It's not the computer. Okay. So meanwhile, I'll just say I want to tell about two tales where. Okay, done that already, and I want to tell you not only how we got to this, but also where it had gone to from the point of our research, and also to tell you about a very interesting question to each of these tales. And the first one is going to be the tale of fault tolerance. So how did it start? So basically, at the point that I entered that room, Michael was very, very interested in the question of how to handle noise in quantum computation. And well, noise is something that is very, very complicated in quantum computation. You can have a variety of things that happens to a single qubit, but let's just think of just the problem of measuring a qubit with constant probability eta. That's the error rate. Each qubit is measured with independent probability eta. And basically, well, that was after the Shor's algorithm, 1 year after that. And And of course, Shor's algorithm was done in an ideal situation of quantum circuits with no error. And Michael had this desire to show that this is, or maybe the thought that that this shouldn't work, and that perhaps noisy quantum computers with any constant eta is just not strong enough. And this is a very natural thing to conjecture, because many such models, as I've learned from Michael, many models express this ability to do ideal computations, which are very strong, but then when you add a little bit of noise, they become worthless. So we set up on this goal, and this was our first paper. This was the paper I was telling you that I was crying about. So that's polynomial simulations of decoherent quantum computers. And how I want to tell you a little bit of how it went. So basically, you should think of a quantum. Say these are n qubits, and suppose these green things are gates. So at first, these qubits are just not correlated, okay? And then the gates basically create entanglement between pairs of qubits, and so these are the clusters of entanglement. So you have small clusters, and then the next set of gates create more and more entanglement, and you get larger clusters of entanglement, and the qubits not participating are just singletons. And so eventually, the whole thing becomes a huge entangled cluster. Now, what happens if you have an error? If you have errors, well, so you start the same way, and you have these clusters. And then suppose these qubits are measured. So that means that this qubit is now disentangled from this qubit. So the clusters become small. They shrink. Now these two qubits are each a cluster of their own. And then you have another set of gates, and the clusters grow, but now they grow not they don't grow as fast. So you get smaller clusters. And this is a random process. So what we did is we managed to map it to some kind of a branching process. And we showed that for eta larger than 0.97, which is very, very large, the entangled clusters remain small. Small being logarithmic, and if the clusters are logarithmic, we can exponential time, that is exponential in the size of the clusters, polynomial time, we can simulate them. So this process is going to be simulatable by a classical computer efficiently. So great. So that was okay. So that was very interesting for us. And we also even did classical simulations, which was a big, I don't know. I was excited about actually seeing how this works in simulations, and we also saw that for eta, which is very small, this doesn't work. And so the important thing here was that it didn't work for small eta. So what we understood is that there is some kind of a competition between two forces. It's not that for every noise the clusters are going to be small, but there is a competition between two sort of equal forces. One is the force of gates that create more and more entanglement, and the other is the force of noise that sort of makes this entanglement go away. And if the gates are working in parallel and the noise is working in parallel, these forces are sort of on equal footing. And there should be some level of noise, if it's small enough, for which the power of the entanglement gates is going to win. And this is what got us actually, Charlie, you were talking about the ability to see that we were wrong and going in the other direction. This was the point where we thought, okay, now this looks like actually it's a very promising sign. Let's do the other direction. And this is when we set off to try to prove the fault tolerance theorem. And sorry. Okay, so at that time, there was these breakthrough discoveries of quantum error correction by Shor and by Steen, and the important insight that came from this discovery was, as John was explaining, with a very fundamental understanding. And this is that quantum information, in order to be protected by an error correcting code, needs to be somehow hidden from the environment in a global way. And why is that? Well, the environment has access to the qubits locally. Let's think that the environment has access to, say, 1 or 2 qubits. Now, the thing is that if the environment has access to, say, 1 or 2 qubits and manages to measure those qubits and get some information about the encoded data, then we cannot recover the encoded data while the environment has this data, because that would be cloning the information, and there is no cloning theorem in quantum. So because quantum information cannot be cloned, it must be that the quantum information to be protected must be protected in a global way. It must be smeared and cannot be accessed by locally. And this is a very fundamental idea that goes into every quantum error correcting code. And what this reminds of is of a paper that was mentioned, that was described by Tal in her talk, the BGW paper, that talks about fault-tolerant distributed computation. Because what we want to do is really perform, somehow distribute the information and perform computation on it in the presence of noise in such a way that locally we will not have access to this information, but it should be spread. It should be actually treated like sharing a secret between many qubits, such that no small group of qubits have access to the secret. Okay, so this is a very strong relation between the BGW paper and the problem of computing in a noisy environment. And this is where this was our starting point, being able to take the idea of secret sharing, and which basically takes a random polynomial, evaluates its value, looks at its values at m different points, and where the secret is actually the value of the polynomial at a different point. And so this was our starting point, and this we made into a quantum code by basically taking a superposition of such polynomials instead of just a random polynomial. And you might recognize the connection between this idea of secret sharing and smearing the information and topological quantum error correcting codes, where also the information is hidden in global degrees of freedom. Okay, so I won't go into exactly how now we took this and made it into the fault tolerance theorem, but just to say that using the polynomial code error correction, or using this code, there's a lot of advantage to use this code because of the strong algebraic structure of this code. Again, as Tal was describing, and this enabled working in a distributed computation way. And this distributed computation way is exactly the notion of fault tolerance. If you distribute the computation between the different parties, then one fault will not propagate to other places in the code, and then we can actually control the propagation of faults, and it can be corrected. Okay, so so this brought us to the threshold theorem, and maybe I will just say very briefly the ingredients of it. The idea is to compute on states encoded on the polynomial code using the polynomial code, apply error correction after every gate so that faults that happened will not propagate too much. So you want to catch them while they're small. And then these encoded operations should be engineered to be fault tolerant, and this fault tolerance is exactly this distributed manner so that faults don't propagate. And once you do this, you can show that if the error rate is below a certain threshold, at a less than some critical rate, constant threshold, the error correction become beneficial. What does it mean becomes beneficial? Means that if you start, so we're doing also harm. We're not doing just good, right? I mean, we're replacing a single qubit, which is faulty, by maybe many qubits, And we're now doing error correction with faulty gates. So we could actually introduce more harm than good. And the point is that if eta is small enough, we actually start gaining, even though we're replacing a single qubit by m qubits. Okay, so and this point where we start gaining is called the break-even point. So showing that we actually get to the break-even point is one thing, but this is not enough, of course. Once we get to the break-even point, this may start improving the error rate, but it's not enough. We have to start maybe from an error rate of some constant, and then we need to get to error rates which are really, really small in order to run long computations. So, so what we did is we basically applied a repetition of this and got a hierarchical structure, and then we got into a big mess, and that was a long way of how to prove this. And luckily, Gash, who analyzed cellular automata and also noisy cellular automata in a variety of ways, provided us with tools to do that, to do the analysis. Now, all this sounds a bit technical. Actually, it was really very beautiful journey involving a lot of excitements and a lot of disappointments also and frustrations. And this is what led us to the threshold theorem. Below a constant threshold, noisy quantum computers can simulate ideal quantum circuits with only polylogarithmic overhead. Okay, so theoretically, this is with sufficiently small noise levels, noise is no longer an obstacle. So that was the result. What happened since? Okay, so the first thing that happened is there were a lot of skepticism about this. And so this picture is you see Michael there, and this is me, and Gil Kalai and Robert Alitsky, two of the leading skeptics in the field. And you can see us, I'm happy also in this picture. And even though this was after a very heated discussion, but very friendly discussion, so they basically claimed that not that the theorem is wrong, but that the noise model is wrong, that this cannot be realistic. And I think this is an extremely important thing to do, right? I mean, as long as this was not realized or is not realized, I think this is one of the most important things to do. We have to be very critical and suspicious about this. So this is one direction, one theme. But then most of the community, I think, treated the threshold theorem and its offsprings, improvements, etc., as a holy grail from the point of view that now this is something that if we can realize, then we could actually have universal quantum computation. And this led to many results of improvements of the fault tolerance constructions. Like John said, these our constructions were very inefficient and bad thresholds, and so improving the threshold and overhead number of qubits and much better quantum error correcting codes, such as the beautiful recent results of the quantum LDPC codes, and handling different types of noise. Again, John described that. And many hardware companies actually, to my very great surprise, and to many other people great surprise, when we started all this, this was the one thing I was told is, look, this is all very interesting, but this is the most theoretical part of theoretical computer science. So I never believed that 30 years ago it would become something practical. That's why I kind of laughed at when you told me that I shouldn't ask about applications. This is, so it's very surprising that it might actually become applicable. So many hardware companies are attempting to realize these quantum fault tolerance. And I think, Michael, this might be a very, very beautiful present to you, also to me, that it seems like very, very soon we are going to see several examples where systems are going beyond the break-even point, meaning that quantum error correction actually helps, and I'm talking about full quantum error correction. So I've cited here Google and Quera and Quantinuum as examples of demonstrations, experiments that actually are really suspiciously close to this point. They're almost there. And I think that at this point, some of the people in this picture are starting to rethink whether their criticism. I mean, it seems like reality is very close to prove that they're wrong.
Having somebody else change their mind doesn't count as humility, right?
I know, but many. I mean, I also changed my mind, not just theirs. So okay. Yeah. So this could be a very nice surprise and a very nice present. But just to say that going beyond the break-even point is not enough, of course, and we have a long, long way to go. We as whoever is trying to build a quantum computer to actually enable realistic applications of an algorithmic application. But going beyond the break-even point would I think constitute a proof of that the concerns are not a full proof, but really an important, very important step that the concerns are not okay. So I promised an open question, and so all these practical implications are really remarkably exciting. But I think not less exciting are the implications to foundations of quantum physics to me. I think that the quantum fault tolerance, the idea of quantum fault tolerance, the possibility of quantum fault tolerance actually raises a question that is very fundamental about the quantum to classical transition. And so why is that? So basically, what the fault tolerance theorem what it says is that all these systems where people are trying to implement quantum fault tolerance, if they succeed, well, all those systems are going to exhibit quantum universality, meaning they're going to be able to exhibit long-range entanglement of many qubits that is controllable and manipulatable and highly complex, and capable of violating the extended Church-Turing thesis. Now, this is very strongly reminiscent of a phase transition. Basically, what we're saying is that below the threshold, the behavior of those systems is going to be completely different than what it would be above it. Below it, it's going to experience this ability to generate and manipulate long-range quantum correlations. Now, this idea of phase transition was explored or was suggested in a paper of mine and in a paper of John and Dennis and Kitaev and Landau as some kind of a percolation, a little bit similar to the branching process. But this is really a toy model. And I think we're very, very far from understanding this phase transition in a deep way. And to me, what do I mean by we're not understanding it? Well, the way it's now understood is as an engineering problem or engineering solution. We're basically saying that there is a different behavior of this macroscopic entanglement. And the reason we're saying this is because of the ability to engineer a universal set of gates and manipulate it. And this is something that's very much coming from computer science. But this phase transition is a physics phenomena. It's a physics phenomena. And this physics phenomena should have a physics description, which it doesn't yet. This physics description, for example, should tell us many things about what is possible and what is not just from the ability to design quantum error correcting codes in various ways, but just by looking at various interactions, physical interactions, and understanding whether those are capable or not capable of, for example, remembering quantum bits for a long time. So in my mind, something of the following something along the lines of this equation which is something like cell automata, but continuous in time, and allowing each of these local operators here. This would be the error local operator, and this would be a local operator responding to non-unitary evolution, which is local, and which includes both the Hamiltonian evolution, but also the ability to remove entropy locally. If we can understand such an equation and understand what kind of operators would allow long-term memory of quantum bits, to me that would be a very interesting thing. And just to say how much we don't understand this. So, for example, we know that quantum fault tolerance can be done in 1D, but we don't know whether a physical 1D system described, say, by a fixed Lindbladian, which is just a non-unitary version of a Hamiltonian, that 1D system described by a fixed Lindbladian could remember a single qubit for a long time. I don't think we know that. If anybody here knows differently, I'd be happy to hear.
What can the non-experts is saying what this equation means?
Yeah. So this rho of t is the state at time t, and basically, if everything were unitary, meaning if there was no noise, then what we would have here is that the evolution in time, the propagation in time of rho is described by some local Hamiltonian acting on this rho. Schrodinger's equation, basically. And what I'm saying here is just replace this local Hamiltonian by a local operator, superoperator, that enables not only interactions between the particles, which is unitary, but also in a continuous manner, removing the entropy away. And then this is a term of errors, which also acts locally. Okay, so it's basically just a way to write down the question of, can we write down a continuous, homogeneous in time and in space evolution, which is, and can we understand what kind of local operators enable memory? And this should have answers not in terms of engineering answers, but it should have answers that I think should include eigenvectors and dynamics and ergodic theory, or not, something, something mathematical that talks about the nature of these matrices. Okay. Okay, so we don't have an answer, I think, to this. And another indication of why I think we really, at least I don't understand this business of what happens at the critical point of the phase transition is that we know, and this is something I don't think I have time to explain now, but I might, I'm happy to tell anybody later. We know that below the phase transition, we don't actually need error correction to achieve very strong quantum computation. If we're below the critical point, below eta critical, we could actually perform Shor's algorithm and factoring without active error correction, basically with just unitary evolution mimicking the quantum error correction, but no putting aside entropy and no basically fresh qubits, etc. And the reason is that Shor's algorithm only requires log depth quantum circuits and classical computation. And in log depth quantum circuits, you don't actually need to do active error correction. It's enough to do just unitary evolution that mimics the error correction. I'm probably saying things that are that I would want to explain this, but I don't think we have time. No, how are we doing with time?
It's
11 what? And how?
You can go 4, and then you can go over.
Okay, so I'll skip that. Whoever's interested, I'm happy to say. But basically, to the expert, this says that Shor's algorithm is in something which is very close to NISQ. And even though it's very close to NISQ devices, meaning it can be done without fresh qubits, the only thing that matters is that we're below the threshold. And so,
Size will still be
no. Size will be polynomial. Size will be
big.
big. No, I'm not saying near term. I'm saying below the threshold. So below the threshold, something very interesting is happening, and it has nothing to do with error correction. It has something to do with propagation of correlations. I don't know. I think that we're missing very much the understanding of this. Okay, so I want to say I want to spend a little bit of time on the second tail, which is tightly related, and that's the tail of quantum verification. It starts at the same picture, but back to the skepticism. Now I'm wearing the hat of the skeptic. So why should we believe all these fairy tales? I mean, this phase transition, well, we still have to jump below it. So why should we believe that we can do that? And this question to me came about in a conversation with Oded and Madhu, and they asked me very vigorously, is there any evidence that, well, they didn't say it in those words, but they basically asked, is there any evidence that the high complexity regime of quantum mechanics is a real thing? Why should we know that? Why should we be so confident that this is possible to reach? And though at first I was sure that it's very easy to come up with a way to convince them, I now understand that there is a reason why. I mean, there's an inherent difficulty in answering this question, and this is because there's an inherent difficulty in testing the high complexity regime of quantum mechanics. And why is that? Well, think of a regular experiment. This is a physics experiment. And how does a regular physics experiment look like? You start from some theory that you want to test. And this is, say, the experiment. And this is a theoretician that computes the prediction of the experiment. And then, in the normal paradigm of experiments, you predict and you compare to the results. And this is how you falsify or test your theory. Now, in the quantum world, if you wanted to test quantum mechanics in many body systems, well, the problem is that you can't make the prediction. That's the whole point in quantum mechanics. The whole point of quantum computers is that we think we cannot simulate many body quantum systems efficiently. And so we cannot make this prediction. And therefore, we cannot actually test exactly those areas in quantum mechanics which are very interesting for us, and those that sort of point at the high complexity. Those are the regimes which we cannot test. So this is a mind-boggling understanding that we cannot efficiently test the high complexity regime of quantum mechanics using the usual predict and compare paradigm. So is it possible to test the high complexity regime at all? So this is a fundamental question. It's fundamental because we can ask, is many body quantum mechanics falsifiable? Experimentally, we should ask, can experimentalists test their systems, claim to be quantum computers in an efficient way or in any reliable way? And cryptographically, how can we safely delegate computations to an untrusted company claiming to do quantum computations if we don't know how to test the results? And so these disturbing questions were a topic of wild discussions in the quantum seminar at the University around the year of 2008. That was 1 year, 2 years before Itamar passed away. Itamar was a philosopher, and he was a philosopher of science and a dear friend, and he was very enthusiastically participating in all these discussions, which of course touch upon very fundamental and philosophical questions of how do we test this mathematical theory, this physical theory. And this is something I want to say that I've learned from Michael in a very deep way, and I've always been inspired by the fact that this question of these connections between physics and computer science they're never separated. They're always sort of not put in a box, but connected very smoothly in a way which, oh, this can be tested using this idea, authentication, as we'll see in a moment, but it's related to a philosophical idea, and the foundations are really, really the motivations for the questions. So, okay, so this was the starting point. This mind, this very disturbing understanding that maybe we haven't tested this high complexity regime of quantum mechanics, and maybe Oded and Madhu are right that we don't have any reason to put all these effort and billions of dollars into this enterprise, etc. Maybe it's just not true. Okay, so how do we test that? Well, handle comes from asking the question of how does Shor's algorithm bypass this predict and compare, this sort of no-go of the predict and compare paradigm pitfall, right? Because Shor's algorithm, if we can run it, is in fact a way to test the high complexity regime of quantum mechanics. So how does it bypass this no-go? So is it understood why it's a no-go? Yeah. I mean, I basically said it's impossible to test the high complexity regime, but if we could run Shor's algorithm, that would be a test.
But how would you know that the machine that was designed, that somebody did not know how to factor, and that it's really running a factoring algorithm? Right?
So it's only the factor.
Why do they
It gives you the factor.
It gives the factors,
So that's it.
but it's not a quantum machine. Somebody solved how to factor in quantum
Right.
mechanics.
So this is
What?
This is assuming it's hard.
Yeah.
Yeah.
But it could be more than that.
The point is that it's under an assumption the factor is hard.
Yeah, it's under the assumption that it's factoring.
Okay, so factoring is hard. So factoring is hard and there's no classical algorithm, but a dedicated hardware machine has been put under, and then what do you do? I mean.
So you're assuming that this is impossible to do. You go to large enough numbers and assuming that this is hard, then that would be.
Hasn't discovered a factoring algorithm and not told us.
Yeah, that's what I meant.
Yeah, right, exactly. Okay, so assuming factoring is hard. So the point is that this factoring, this basically test or verification of factoring is a very, very primitive example of interactive proofs, which is another topic that Michael has contributed in extremely foundational ways. So why is that? Well, interactive proofs are in this model where a weak BPP verifier interacts with an all-powerful prover, but now replace the all-powerful prover with in this model we know that we can prove a computationally weak verifier can get convinced of highly complex claims without knowing how to prove them. So this makes the power of the verifier much stronger. This interaction, but if you look at this example of Shor's algorithm, it is a very rudimentary example of an interactive proof. Instead of the all-powerful prover, we have a BQP prover who factors and then sends with one round of interaction the factors, and then there is a very simple verification process of just multiply P and Q to know if it's equal to N. Okay, so and this is outside of the predict and compare paradigm. Okay. So now why not do it more generally and have a general interactive proof where the quantum computer is the prover and the verifier is a classical weak machine, and the experiment, the test, is interactive. And this is really what we did, and we constructed such a protocol. We couldn't do that with where the verifier was just classical. So we had to add a few qubits to the verifier. So the verifier is not completely classical, it's just slightly quantum. So we have to trust, say, 3 qubits. And then we managed to prove that a BQP prover can prove any quantum circuit, any polynomial quantum circuit, to a BPP plus O of 1 qubits verifier. The proof is based, as I said, on quantum cryptography. Again, another topic which we'll not have time to describe the contribution of Michael to. But let me just give a very one-sentence explanation of how it works. Essentially, the idea is that the verifier picks a random error-correcting code and encodes the information on this random error-correcting code that the prover, the quantum computer, doesn't know the code. And using the classical interaction, the verifier helps the prover perform the computation without knowing the code on this random error correcting code. And then when the verifier gets the state, it can actually test that, that the state is in the code, even though it cannot verify that the propagation within the code is correct. Okay? Because that's too complex. So that's the idea. And so any quantum evolution can be verified efficiently by a classical prover with a few qubits. What happened since? A lot. Can these be done by a completely classical verifier? That's an obvious question. And that led both, is Umesh already here? Not yet, but he will be talking about this. That led Umesh and with Reinhard and Unger show that this can be done classically in the model of multi-provers, adding a prover so that basically one can interrogate. So two provers are stronger than one, as again showed by this paper introducing MIP of Michael and friends. I'm sorry? What? I know. This is after they separated. Here is before. So adding this prover, and in this case, they're entangled. These provers allows this verification with only classical interaction. And so this MIP star approach led to many follow-ups, quantum certificates. Again, Umesh will talk a little bit about it, I'm sure, and a variant of quantum PCP, and even to the MIP star equals RE result. And then a different direction, a different branch of evolution was Umila's wonderful result that shows a protocol for a single prover managing to interact only classically with the verifier, a single prover managing to interact only classically with the verifier, but under a computational hardness assumption of the LWE. And it still remains a question of, can verification be done by a single classical verifier? And is there a quantum variant of the PCP theorem? And there are many other problems related. Okay, I want to talk about one problem that. 30 seconds about the open question I actually really like that comes out of it is this actually suggests a new type of experiments. Because with this interaction between the verifier and the prover, we actually can think of new types of experiments in which instead of actually having this predict and compare paradigm, we can add structured interactions along the lines of interactive proofs. And maybe we can save a lot in the resources and do much more with these interactive experiments. And indeed, we showed that in a recent paper where you can actually save using these interactions exponentially in the amount of resources. And this opens up basically a new direction. Instead of looking for quantum advantage in algorithms, you can actually look for quantum advantages in experiments. Looking at trying to save the resources, maybe exponentially, in the resources that are required for precision measurements, etc. So I think this is a very interesting direction. Okay, so yeah.
So what's can you say? So it's not a predict and compare. So you don't redo it. You do something else.
Mm-hmm. What do you do? For example, you could, if you wanted to. If you had a lot of power, like a quantum computer on the side, the experimentalist could have a quantum computer on the side and another system that you wanted to maybe perform a measurement. Then you could think of entangling this quantum computer with a system. You could, and this was actually done. Google actually had an experiment doing such a very simple example of such a saving in which you entangle a single qubit to the system that you want to measure. And then by entangling this single qubit performs, acts as a memory. And then this memory sort of correlates between the different parts, the different applications of the experiments on that system. And somehow this gives you a lot of mileage that you wouldn't be able to do if you just had, the regular access of measuring that system, throwing the system away, measuring it again, and then doing classical post-processing. So
in your paper, the one that you referred to a few slides ago, where the verifier, I guess he was on the other side, he had a qubit. So he was classical, but he had a qubit.
Right.
And the amount of time that he was taking was as long as the computation.
right.
Right. Here, the amount of time is going to be shorter, because you are again going to this place where the verifier is not completely classical, but he's able to do some sort of quantity thing in order to have this new type of verification.
Right.
But is the point that the time, I guess it's a different type of.
So what I'm comparing, what I'm comparing is the usual type of experiments done now in the lab, in various labs, in which you basically want to test a physical system. You perform some measurement on it, you get the results, and you throw it away. You basically restart the whole system, and then you do post-processing on the results. So it's not verifying a certain computation. You just want to basically compute a certain function of the system. For example, you have a lattice, you want to understand its structure. This is a function where the input is a physical system. Now, instead, you could actually perform a quantum algorithm to do that, meaning you have the system, maybe you have another qubit or two on the side, maybe you have n, and you can sort of generate a complicated state combined with the system that you want to measure and the extra quantum here. And if you do it very cleverly, you could save a lot in the resources compared to what you would have done if you didn't think of this complicated interactive experiment and you just did the simple things.
So this, what I would call a verifier, the one on the right, the amount of work they're going to do is going to be less than.
Right. Yes.
At the end, that's what you're trying to get to.
Yeah, I'm trying to save on resources and also on time, as Thomas.
No, on time you're clearly not saying.
But I'm trying. Okay, so just to say, Vicky, thank you very much for all your support and all the lovely things that you've taught me. And I wish both of us that we enter several at least, new doors, new path through that door, and go into very exciting and interesting journeys. Thanks.
So just reminding everyone that we're going for the photo through those doors to the other side, through that door to the other side. And since we are 30 minutes late, we will start at 3:55. Okay? 3:55, everyone.